a talk here. And Zhou got his PhD degree in Tsinghua University in 2014. And then he became a postdoc researcher at the Institute for Theoretical Physics at Frankfurt. From 2017, he was a research fellow, and in 2021, he was a fellow and lead the AI for Science group at FIAS Frankfurt. And his research actually covers many aspects related to high energy nuclear physics. And today he will talk exploration the matter in extreme conditions with machine learning. Thank you.
So I can start now, right?
Yes.
Okay, thank you very much. So first, many thanks for all your coming, and then many thanks to the organizers, thanks to Nu, Yi-Ying, and Hui Chao for inviting me here. And also many thanks to all the lovely collaborators of me to help us in constructing the content of this talk. So today I'm very glad to introduce you some of our recent research endeavors that's implementing this machine learning perspectives into the exploration of acoustic matter in extremes. So I hope with this talk, I can kind of motivate some of the students to be aware, also to getting interested in such an interdisciplinary direction. And on the other hand, I hope this might inspire you to think about your research problem at hand, can give it a try from such a different perspective. So here, this is the outline of my talk. So I will first reiterate this basic physical overall picture. So you might heard already many times. And after that, I will just give a very short, very crash course about the related AI, machine learning, and deep learning techniques. After that, we will look into how we can play around with these techniques to help our exploration for acoustic matter from those different sectors. So from the heavy ancylation sector, the Lattice related calculations or neutron star study side. And in the end, I will make a summary. Okay, so the general motivation lies in our long quest to understand acoustic matter in extreme. So this is basically a very many-body task, similar to the condensed matter physics study. So we try to figure out the different physics and the properties of acoustic matter, along with different external parameters like temperature or pressure, or might also be some other dimensions, for example, the magnetic field. So in general, we know matter in extreme can reveal its constituents. So imagine if we heat the nuclear matter up to high temperatures, then gradually we will have the mesons and the resonances to be excited out. And to some extent, they may overlap once this is within a finite size system. And the same can happen if we compress the nuclear matter up to high densities. And once there is overlapping between the hadrons, their constituent quarks and gluons can move freely inside a relatively larger area. And they would not be confined into the hadronic bag anymore. So consequently, we will have such a new state of acoustic matter. This is with the elementary quarks and gluons to be their basic degree of freedom. And people call this quark-gluon plasma. It's a deconfined acoustic matter state. This is basically following the famous quote from T.D. Lee. So this is in around 50 years ago, that if we can distribute a high energy or a high nuclear matter density inside a large volume, then we can get a chance to explore the interesting phenomena to study such kind of extreme acoustic matter. And this is also motivating our heavy ancylation program to construct such a heating or compressing machine in the terrestrial laboratories. And indeed, we accumulated some knowledge about the acoustic matter in extreme. So here shows you our current sketch, the conjecture for acoustic phase map, along with temperature and baryon chemical potential in this x-axis. So we know that at vanishing or the very small baryon chemical potential, it's already well kind of confirmed from the Lattice acoustic study that the hadronic matter will turn from a dilute hadronic gas to the deconfined quark-gluon plasma along with increasing temperature. And this is via a smooth crossover manner, and the transition happened at around 150 to 160 MeV. And from different model studies, we are kind of expect that would be a first order phase transition between the normal nuclear matter and the quark-gluon plasma. So this will imply there might be some critical endpoint somewhere to separate these two different scenarios. But today, whatever the location or even the existence of this point, and also the properties of different phases is quite unclear yet, because the Lattice study set will be hindered from the fermionic sign problem once we're going to the high density region. And there we have to rely on, for example, the effective model study or the direct experimental study. And if we look into the sky, we can also get a chance to study the cold and the dense nuclear matter in terms of neutron star. And there we can get some astronomical observationals to help our constraining there. And the study of the extreme QC matter is also relevant for the cosmology, because the entire universe lies right inside such a quark-gluon plasma state in a few microseconds after the Big Bang. And I would say today, we are right in the area to get further deep understanding into the QCD extreme properties, because from the different sectors we just mentioned, we are all having some rapid advancement. For example, in the nucleation side, we are now entering the precision area because we are having a lot of the upgrade to be scheduled, and we will have a lot of the high luminosity infrastructure will be established. So there we can get more and more high statistical measurement. And then theoretically, the first principle lattice field calculation will also benefit from today's the numerical algorithmic development and also the hardwares growing up, for example, the GPU usage. Then in neutron star sector, we are having the, sorry, let me put it upstairs. We are having this discovery frontier because of the rapid development of gravitational wave analysis and the multi-messenger astronomy observations. So we will get more and more constraints in this region. So essentially a joint effort across these different sectors will give us a more complete or complementary understanding. But because of the involved complexities or the large computational need in some of the involved tasks, the new computational paradigms from AI or machine learning, deep learning algorithms can enter the game directly and provide a practically very efficient perspective. So indeed, this is the case. Actually, this is just like 100 years ago, the electricity to our life. Today, those AI techniques is now penetrating and transforming our, not only the everyday life, but also this frontier scientific research. Like here are some examples about the mathematical knot theory proving, and this is for the geoscience forecasting, and this is for the particle, the high energy physics, and this is for the coil design to achieve the fusion reactor, and this is the molecular dynamic speeding up. So they all sound very magic, but their underlying engine is actually rooted inside the combinations of several mathematical strategies. Like quite often you will see that a lot of the studies are using deep neural networks. So they are actually providing us a universal function approximator. So this got well approved in mathematics already, that you can use that to represent any well-behaved functions to any accuracy desired. And then with the differentiable programming strategy, you can efficiently optimize those involved representations, those neural networks. For example, using the backpropagation together with gradient descent. And by doing this, the GPU can be properly applied because this involved operations is just some linear algebraic, for example, the matrix multiplication. So they just fit very well into the graphic card. Okay, so now to set us on the same wavelength, I will very briefly introduce some of the jargons there underlying workings. First, machine learning. So what is it? So basically, in the entry-level perspective, you can understand this to be a function fitting. Just the function being involved might be very implicit, like we do not know how to summarize, how to come up with such an implicit expression to do this image recognition task. But we are sure there are some underlying math for this job, and there are also some neural network to be able to well approximate it because of the universality theorem we just mentioned. And by training, we can hopefully find out the pertinent network parameters. For example, if you use some fixed structure neural network, by varying the parameters, we actually have a functional because you can get a set of functions. And for each of them, we can evaluate the goodness of this function on the training data. So you have some loss function, you can calculate it. And based upon this goodness, you can pick up the best one or the good ones, applying some optimization algorithm. Then together with some generalization consideration, you will find the picked function can also do a good job in the testing stage on some unseen data. So that's it. So we see for machine learning, the key concept is just these four components: the model, the loss function, the data, and optimization. And the model here can be many things, not only limited to neural network. For example, this can be some simple linear expression or support vector machine or Gaussian processes, can even be some physical model simulations, some pieces of code, or this can be some ODE solver or PD systems. And by varying different components, you can get different learning algorithms here. So if you choose neural network to be a model here, then the functional is constructed by composing many simple building blocks iteratively. And this building block is just performing the linear affine transformation together with a nonlinear activation function. So you can also call it a layer. And for a simple neural network, such as here, you can write down explicitly this parameterization. So that's the linear transformation, the nonlinear activation function, then you repeat it. Here, this compositionality can set in a key success feature of the deep learning. That's called its ability of doing hierarchical representation learning. So here, this is just a fancy name to confuse you a little bit. What does that mean? Basically, you will observe for a lot of the deep neural network training, it will use it for front layer, the shallow layer, to process the pixel level information, trying to first detect the edge or the orientation, and then gradually it will combine them into some more complicated features. And in the end, it will use its deeper layer to target at, for example, the shapes or the objects until the final semantic meaning. So this is very similar to the compositionality feature in physical world, right? And people say this resembles the renormalization group procedure in physics, because both of them, the representation learning or the renormalization group, they're both trying to remove the redundant high order information, trying to abstract the very abstract or the more informative or the emergent degree of freedom. And in this image recognition task, this training might be locating this final semantic labeling, but if you do the similar calculation on a statistical system, this might be calculating the order parameter for some field configurations. And besides such a compositionality features, we also have some other physical priors can be embedded inside the network designing, for example, the locality or the translational invariance. And accordingly, we have this kind of convolutional neural network to really respect such a translation invariance and the locality. And this got proven to be very powerful, very good at the pattern recognition. So basically, we say the physical laws is very important in the working of such learning algorithms. Then besides this hierarchical representation learning feature of deep learning, another key successful reason for that is the differentiable programming strategy. And if you want to use just one sentence to abstract deep learning, that would be it's composing differentiable components into a computer program, for example, a deep neural network. Then we can use the gradient to optimize it. And to evaluate this gradient, you can use the automatic differentiation. This is one way to achieve this differentiable programming. Another fancy name to confuse it a little bit. So basically, this is just applying the chain rule to calculate the derivative. But indeed, this got proven to be much more advantageous than the numerical differentiation or the symbolic derivation for this calculation. And it can also guarantee the machinery precision for its estimation on this derivative. And the powerfulness of this technique comes from the granularity or modularity. That means you can define by yourself inside this computational graph your own intermediate operation node. For example, this can be some simple mathematical operations, the summation, subtraction, exponential. Can also be some algebraic operation like the eigensolver or the SVD decomposition. This can also be, as we mentioned, can also be some black box model simulations or some PDE systems. And what you only need to provide is the linear response of this node. So just provide the Jacobian between this input and output. With that, you can perform the chain rule. So in a reverse mode, to calculate the automatic differentiation, you just repeat this vector Jacobian multiplication from the end. So this is the end, right? Till the desired variable or parameters. And the easy way to look at it is to introduce a joint variable that's defined as the derivative of your final objective with respect to the output of the intermediate node. And the propagation of such a joint is just multiplying the Jacobian in a backward fashion. And then any gradient of the variable or parameters is just multiplying the gradient of that associated node to this Jacobian. Okay, so when you go to a much more complicated computational graph, this is also achievable. Like here, this is a graph with the branches. The thing you need to do is just sort first this family tree, then you locally take into account the contribution from all your child. Then you can arrive at the same calculation for this gradient evaluation. With the gradient got, now you can perform the optimization on your learning algorithms. So the above mentioned stuff is using the perspective of the function fitting, but this is not the full story. The learning algorithm is actually more than the function fitting. There are actually two kinds of perspectives. One is called this discriminative learning, usually in a supervised manner. So the aim or the purpose usually is trying to get a conditional probability, this P of y given x. So for some input x, you want to figure out its corresponding labels, this y. This can be some class identities. Then you are doing this classification. This can also be some continuous or any kind of values. Then you are doing this regression. So basically, you can see this is a function fitting. And with that, you can do the prediction after the training on some unseen data set. But there's also another perspective, is this generative learning. There, the purpose is trying to learn a joint probability. So for example, you do not have any labels, or you do not have the structured correlation between them, between the labels and the data. And what you want to do, for example, you want to generate a new picture. You want to sample a new field configurations, obeying some desired distribution. And in physics, such kind of joint probability is very similar to the partition function. We know partition function contains all the information of the system. And here similar. So once you are able to sample from such a joint probability, and you can get a higher level understanding of your system. And in the community, people always use this quote from Richard Feynman to kind of advertise the generative modeling, that what I cannot create, I do not understand. And indeed, imagine if you want to write a paper, this is somehow more difficult than just to read the same paper, right? Okay, so with this very crash course being armed with, let's look at how we can play around with these techniques. So we will ask some questions around the three sectors that in nuclear accretion side, will the early time dynamics information survive until the end, and how we can effectively connect the experiment to the theory or the model. And then what's the current heavy accretion observable, for example, in the low energy keys would imply for the dense matter equation of state. So how we can use deep learning trying to figure out some knowledge there. In the lattice calculation sector, we know the heavier barrier for the calculations would be the observable evaluation and the field configuration generation. So is it possible to use machine learning to provide some toolbox? And in the data analysis sector, we are focusing on the inverse problem solving, that how we can efficiently convert the lattice data into some real-time physics. In the neutron star sector, we're asking how we can maximally exploit the astronomy observation into the knowledge about the Q systematic extremes. So what the time? Okay, so now let's look into those different projects. First, in heavy accretion side, this is about the hot matter bulk property identification from the accretion using deep learning. So there, basically, by colliding the heavy nuclei, we want to achieve the extreme conditions to form such a new the new kind of QC matter in extremes. But the practical challenge is that the whole accretion process is a highly dynamical, very complicated, and super fast evolving process. So even though the deconfined quark-gluon plasma state indeed might be formed by the accretion, it will undergo the rapid expansion and cooling down to some extent. Their degree of freedom will confine again into the hadrons. So in the end, experimentally, what we can only resolve is the finally emitted hadrons or their decay products, like we can measure their mass, their identity, or their momentum information, but we get no direct access to this early time dynamics, to this well-cooked hot soup, but we can only smell from it. And furthermore, theoretically, we have a lot of uncertainties being involved inside our dynamical description for the accretion process. For example, the initial fluctuation, the matter's bulk property, transport property, and some other hyperparameters, because we do not have the 100% theoretical guarantee for those knowledge. So these are called uncertainties, and they may entangle with each other, also entangle with the final observables. Then from those final observables, we call it the smell, how we can get some fundamental physics about this early time well-cooked soup. This is challenging for a long while. And this can be viewed as an inverse problem, actually, because given those different physical setups, like the bulk matter property, the transport coefficient, and the initial fluctuations, then we have the well-developed computational models to simulate the accretion process and get the final state information. But now, given only limited and very noisy measurement on the right, how we can get robust inference on some of the CAD physics, this is not trivial. And Bayesian inference can provide a statistical method here. And later I will also show you one of our recent work using this. By the way, could you still hear me? My iPhone was just run out of the charge.
I hear you clearly.
Okay, let me just speak. Okay, could you hear me now?
Yes.
Okay, good. So alternatively, we're taking a different perspective, and we ask the question, are there inverse mapping from this final state information to one of the CAD physics? And this inverse mapping is definitely not that explicit because we do not know how to disentangle those influence. So this is similar to the image recognition task. There, the underlying math is also very implicit, but inspired from the success of computer vision. So we propose to use convolutional neural network here to learn this mapping directly in the sense of big data. So we can prepare the training data from state-of-the-art computational models, and by varying the parameters involved, we can introduce the diversity. And for each of those simulations, we record final state information like the pion spectra, use that as the input to the network. This is similar to the image to the network. And we train the network to classify the involved QC transition is a crossover of first order. This basically is embedded inside the equation of state as one of the very desired QCD bulk matter properties. Okay, so briefly speaking, what we are doing here is supervised training for a classification task based upon a huge training data that can be generated by state-of-the-art, for example, the event-by-event hydrodynamic simulations. But before further going, we need to be aware that such a problem setup might be nonsense, because you can always create some training data arbitrarily and input that into the network. The neural network here is just similar to an omnivorous animal. It can eat anything, like it can be grass in, milk out, but it can also be garbage in, garbage out. For example, you cannot ask the question, could you train this network to classify the CPU types you have been using in generating this final state information? Makes no sense, right? So here similar, because the imprint of this early time dynamics might be already fully washed out by the whole collision evolution. So this could be the case. Then the key point is to really check the testing performance. So after the training, we should monitor their performance on some unseen, very different event to see if it's still making sense to give us some predictions. If indeed you can get some positive testing performance, that would first mean the problem setup here makes sense, and the fingerprint of this early time QCD transition information is still there inside the final state information. And with the network, we can figure it out. So trying to make the testing dataset to be very different, we actually tune the initial fluctuation. We also tune different values for the transport coefficient. We even used a different hydrodynamic package. And for those testing datasets, we see using the conventional observables, we definitely, it's impossible to make a distinguishment. This is strongly depending on the initial fluctuation and their other uncertainties. So you see here, the blank one is for the crossover, the red ones are for the first order phase transition using this elliptic flow or the mean PT spec or the normalized PT spectrum. It's not possible to distinguish them. Then we use the trained convolutional neural network. We achieved on average 95% event by event classification accuracy on this different testing data set. And this performance is also robust against whatever the initial fluctuations or some other uncertainties like the transport coefficient. That would mean information about the early time dynamics can survive into the end of the hydrodynamic evolution. So the caveat here is we didn't include the afterburner hadronic on the hydrodynamic level. And with the raw spectra from this hydrodynamic simulation, we can decode out what's the QCD transition information you have been using. And this decoding is immune to the evolution's other hyperparameters. Okay, as we said, we didn't include other physical effects for the collision. So we further deepened this idea, push it into more realistic cases, like consider the afterburner hadronic cascade using the URCOMD simulation, and also consider the possibility to take the possibility of the non-equilibrium transition, like the spinodal can induce some baryon clapping. Then we also included the detector effect. So this will allow the direct usage of the hits or the tracks from the detectors to be the input of the learning algorithms. And there, accordingly, we developed the point net-based models. So basically, we showed that this is possible to using deep neural network to make a solid bridge in connecting the experiment to the theory or the model simulations. So in following, I will further introduce a little bit about this point net-based model, because I think this might be interesting for some of our experimentalist friends to think about in future about the online event characterization. And this work is mainly done by our excellent PhD student, Manjunath OK. By the way, just one private sentence. So he's now getting his thesis writing and are searching for postdoc positions. And this excellent young man is quite familiar with both the theory simulation and experimental setup, and also the learning algorithm stuff. Okay, so basically, when we work directly on the experimental data from detector, if we still use the image-like record, for example, the histogram of the particles, then this record will be super sparse. So to handle such a very sparse matrix, you will waste a lot of the memories and the computational demand. So that's not efficient at all. Actually, such a data from the detector has inherently a point cloud structure, means it's a collection of particles in some attribution space, like here. So you can record it as a two-dimensional array. Each row is a point of particles, and each column is its attributes, for example, its charge, the position, or the momentum. And one key feature of such a point cloud structure is one representation here should be invariant under the permutation. So this is an unordered list. By changing the order of different particles, that's still one event, right? So accordingly, the point net is one kind of neural network structure to learn directly based upon this point cloud representation. It can respect this order invariance naturally. So that's the reason why such point net-based models might be very useful in the particle physics and in nuclear physics, trying to work directly on the detector output. And for a demonstration purpose, we considered here the CBM experiment. And the CBM detector is currently being constructed for the FAIR and JSI. And one key feature of CBM detector is it will have the very high event rate and the trigger rate. So roughly it will produce 1 terabyte raw data per second online. So any kind of algorithm to speed up the event analysis would be very helpful. That's the CBM challenge. And on the right, you see simulated events from the sub-detector system of CBM. So that's the STS, the silicon tracking system, together with the micro-vortex detector. So they both lie inside the dipole of magnet right after the target. And to show you how we can directly work on this detector output, that's the hits and tracks. So we use the impact parameter estimation as an example. The impact parameter actually is very essential in understanding the event geometry and for further analysis. But experimentally, we have no real control over this impact parameter. And this is also not measurable in experiment. So usually some final state information like the charge multiplicity or the spectator deposition will be used within some model simulation, for example, the Monte Carlo Global, to define some centrality classes. And from there, only some likely distribution of this impact parameter can be get for some given centrality beams. But this is not for individual events estimation and not accurate at all. For example, here you see the histogram of the charge particles tracks, the number of charge particle tracks as function of impact parameter. By the way, those events are simulated from URQMD. So we see at a fixed track multiplicity, there is a very wide spread of their possible impact parameter. The spread can be 4 to 5 Fermi even. So to get some accurate impact parameter estimation on event by event basis, this is a non-trivial task. And this is also constructing us an inverse problem again, because specify the impact parameter, we can just apply the model simulation, for example, URQMD, together with the CBM route for the detector simulation, we can generate a lot of the events. But given only the hits and tracks information from the detector, how we can get the corresponding information about the impact parameter, this is an inverse problem we are asking here. And again, we are utilizing the supervised learning strategy. So we will provide some training data from the URQMD and the CBM route simulation. And there, the final record would be the hits and tracks inside the detector. And we build such point net-based models to construct us the beam meter, the impact parameter meter. The structure looks like here. So basically the tracks and the hits information are taken as the inputs, and the output would be the impact parameter. So for the details of this network structure, I will skip that. You can resort to our paper if you are interested in. And to test the sensitivity of different data types, we developed 4 different models. So here the M hits And SHIS means we are using the hits information inside the MVD detector or STS detector. And this MS tracks means we are using the tracks information that's reconstructed from the hits inside the MVD and the STS detector. And the fourth model is using the combination of the hits and tracks information. So this will definitely require more parameters. But to provide a reference or baseline, we also developed a very simple polynomial fit that's using the third order polynomial fit to connect the multiplicity and the impact parameter also on event by event basis. And the training dataset is, as we said, it's generated from URCMD and CBM root. We provided around, this is 100,000 gold 10 GeV collision events with different centralities. And we use that as the training set. After training, we test it on some different testing events. So here shows you the results. So first about its resolution. We know that the resolution can be indicated by the spread of your prediction. So we can calculate their relative precision and such a standard deviation of the distribution of your prediction error divided by the ground truth of the impact parameter. So we see that at central collisions, the very simple polynomial fit, these gray curves, they are definitely FIAS because it's increasing up to 200%, means they are very uncertain about their prediction. But the point net, these deep learning based models, those colored lines, they are giving the prediction spread around 0.8. And this will further drop to 50%, 0.5. This is already a quite reasonable prediction once the collision event is with B being larger than 1 Fermi. But within 2 to 15 Fermi for the impact parameter, the prediction spread from whatever the polynomial fit and the deep learning models, they are quite similar. However, when we want to construct some meter, we do not only care the precision, we also care the accuracy, right? So we want this prediction to be also accurate, meanwhile it's very certain. So this can be quantified by the mean prediction error as function of impact parameter here. So we see that in the region of B between 2 to 14 Fermi, the polynomial fit, these gray curves, they are quite fluctuating. So they have very poor accuracy. But the deep learning based models, they are very, very accurate. So the prediction error is around from minus 0.3 Fermi to 0.2 Fermi. So a joint evaluation from these two measures definitely would prefer the B meter, the impact parameter construction from the deep learning models. This is much more evidence if we go to a more realistic case. There, the collision events should be distributed as this BDB. So here we see the fluctuation of the polynomial fit is much more evident. And another highlight I want to put here is the speed of the train model in estimating the B is very fast. Actually, we didn't do any optimization on the speed, and using only 1 game GPU card, we can achieve around 1,000 events per second for the event analysis. So this can be further improved for sure. Okay. So let's back to a little bit about the extreme matter properties extraction from heavy ion collisions. I mentioned that Bayesian inference is also providing a nice statistical method. And recently we have such a project also done with Majunath OK and Jan Steinheimer. We asked the question how the current heavy ion collision measurement in the intermediate beam energies would imply for the high density equation of state. We know for those kind of low energy heavy ion collisions, the hadronic cascade phase, including the spectator effects, they should be dominant because the interpenetration time is very long, right? Then we do not have well separation between the initial compression effect and the expansion phase. So that's the reason we are taking this URCMD simulation to be the physical model here. And by the way, the URCMD simulation recently got augmented by Dr. Jan Steinheimer to be able to incorporate any kind of density-dependent equation of state. So you can introduce some density-dependent mean field potential to enter inside this quantum molecular dynamics part for your simulation. And basically, you're just solving your equations of motion for particles, and you introduce some mean field potentials to guidance the change of the momentum there. And for the purpose of the extraction of this density dependency, we parameterize this mean field potential with such a seventh order polynomials. And given such a density dependent potential, you can evaluate directly their equation of states. You calculate the pressure using this integration. And here you show some examples from this polynomial fit. This is a polynomial parameterization. And we use this parameterization only for the density range from 2 to 6 times saturation density, because for lower density values, for example, up to twice saturation density, we can use the chiral mean field fit, or you can use some other constraint from the low energy experiment measurement, or using the effective chiral field calculation, whatever. And to perform the Bayesian inference, we also need some evidence, some experimental observables. And here in this work, we chose the elliptic flow and the mean transverse kinetic energy for protons at gold-gold collisions with beam energies ranging from 2 to 10 GeV. So here you see the data, and also you see the simulation from URCMD implemented. You can think of those simulations to be our starting point for the Bayesian inference, take it as the prior, or you can take it as the training data set to get some model emulator. Later, this will be needed about the MC exploration stage. And by the way, one advantage taking purely this URCMD simulation as the physical model here is that the whole collision evolution can be consistently described by just one model. You don't need some other hyperparameters. Only these 7 parameters need to be adjusted to match this data. So that's one advantage. But for those 7 parameters inside this polynomial expression, even if we only consider, for example, roughly 10 possibilities of each of the parameters, in total, you will come up with 10 to 7. That's 10 million different possibilities. And for each of them, if you require some statistics, for example, thousands or 10,000s, in the end, you will need to run, that's 10 to 11 simulations. That's definitely impossible to perform a brute force searching inside this parameter space. So luckily, the savior here is again the machine learning. So we can resort to emulator with Gaussian process. You just understand it as a specific functional format. The input is those parameters, and the output is the physical observables. So usually you need to run the simulation to get it. But here you can train a Gaussian process to really give you some very fast surrogate model. And specifically, Gaussian process is a stochastic process. It's a stochastic functional that can map input into some normally distributed outputs. This can get fully specified by a mean and a covariance function. And we randomly sampled 200 equation of state from that polynomial expression, implement that into the URCMD simulation, get the events and get the physical observables. Then we train the Gaussian process. And here you see the trained Gaussian process's performance on some testing data set. So again, this is the testing performance. On general, we see this determination of coefficient, the R-square value is 0.9. So the performance is quite good. So we can use that as the instead for the model simulation. We don't need to run the model simulations always when you do the exploration for the posterior later. So with this well prepared, now we can perform the Bayesian inference using the Markov chain Monte Carlo to explore the posterior. So by Bayes' theorem, we know that the posterior distribution of the model parameters given the evidence is proportional to the likelihood times the prior. And the likelihood here is quantifying how well these chosen parameters can accommodate those evidence within the model or within this Gaussian process emulator. And the prior here can encode our initial belief or knowledge into those model parameters. So here we are taking the Gaussian distribution, trying to introduce some ignorance of this expression. And to justify our Bayesian inference pipeline here, we first performed several closure tests. So there we just assume some random equation of state to be the ground truth and implement that into the URComD simulation, get the physical observables, use that as the mock data to perform the Bayesian inference. And then you can compare your reconstruction to the ground truth you have been using. So here shows you some randomly chosen cases. The color contour here is indicating the probability of the posterior on these potential values at different density. And being plotted, there are also two curves from the reconstruction. One is this mean curve, one is this MAP, the maximum a posterior curve. So we see in general, the reconstruction reproduces very well the ground truth up to 4 times saturation density. That would first indicate the used observable, those elliptic flow and the mean MT, indeed contains information about the high density equation of state in this range. And once we are going beyond this range, we see the reconstruction is showing larger uncertainties. But looking at the two curves, the mean and MAP curves, they are still quite closely following the ground truth trend. And to test the sensitivity of the inference results with the observables we have been choosing, we specifically did a different closure test. That's on the right. We purposely removed the first 2 points of this mean MT observationals. So that's around 4 and 4 point something collision energies. You see that the results showing some difference. So first, the general agreement between the reconstruction and the ground truth is decreasing compared to the 15 data case. So we call the full usage of data to be 15 data scenario, and removing these 2 points, we call this a 13 data scenario. You see the agreement is decreasing, means this 2 point or these 2 collision energies measurement of mean PT is very important in constraining our knowledge about the high density equation of state. Even though there is not reaching the very high density, but the compromisement inside this fitting matters a lot. And with this well verified, we can do the inference using the real experimental data. Here shows you the results, again, for the 15 data case and the 13 data case. So first we say, using these observables, indeed we get some reasonable constraint. So the band is not that big. And using the 13 data point case, we observe a much larger uncertainties, especially in the high density region. That's also making sense, right? We are moving 2 points from the evidence. And if we insert back these reconstructions into the URComD simulation, we can check its description ability against this evidence. So it's shown here. So again, for the 15 data case in red and the 13 data case in black. So generally we say, if we remove these 2 points of the mean MT, the reconstruction, these blank curves, they will give us a better description for the elliptic flow at higher energies. Meanwhile, it's showing a smaller mean MT. That's making sense, right? You are having a less expansion. And this is also manifested inside its equation of state. You can see there is a softening phenomenon happened here. And usually people say the directed flow, the V1, can be a very sensitive probe for the high density equation of state. But because of the statistics, it's very high if you simulate this V1. So we didn't use that, even though we have those experimental measurements, but we didn't use that as the evidence. What we're doing is we use only the V2 and MT to constrain the equation of state. And after the inference, we insert this reconstruction into the simulation to check its predictability. So here you see the comparison between the simulation with this inferred the equation of state together with the data. So we see our reconstruction can very well describe the data, especially for the case using the 15 data points, the red curves. That would mean if those measurements are reliable, this would prefer the equation of state reconstructed from the full usage of the data. And to let you to have a better feeling about this reconstructed equation of state, here we calculated its speed of sound square as function of energy density. And we are only plotting these mean curves for the two scenarios, the 15 points and 13 points. And being compared, there's also a band. This is from a recent work. That's the constraint from the binary neutron star mergers. That's a work done in Frankfurt by Luciano. So we see that the reconstruction of the equation of state from our BH inference using the full observable is kind of very compatible to the astronomy constraint here. And if we remove the 2 points for the mean MT, you observe such a drastic drop and this high energy density for the equation of states. This might be related to the phase transition, that might also relate to some tension for the measurement here, or the tension between our used UR-COMD simulation in describing the data here. Okay, so this is basically the message I want to deliver to you from this project. And now let's enter into the lattice related study. Let me look at the time. Okay, I have to really run it very fast. So first about the basic application of the machine learning inside the lattice calculation for QFT or some many-body system. And in this work, we demonstrated on 1+1 dimensional complex scalar field theory that the deep neural network is capable of capturing the phase identities of your system. So this is at the finite temperature and finite chemical potential. So there is the condensed phase and a silver blaze phase. So using the network is able to capture this phase identity, but the training happens only in the very two end. And then the neural network is also able to capture the calculation of the physical observables. So here we showed this phi square, the squared field calculation. This is a very nonlinear calculation based upon this lattice field configuration input. And again, the training happens only in this very far away two end, but the prediction result is very good, even far beyond these two training points. That means the network is able to perform the nonlinear interpolation very efficiently. And besides this regressive analysis, we also performed a generative modeling for this field system. We tried to generate new field configurations to obey the desired distribution. So very surprisingly, we find that the implicit constraint, some divergence expressions, can be automatically fulfilled by this generative modeling. Meanwhile, the distribution is reproduced very well. So we further explored such a generative perspective into the numerical calculation on many-body system in a general sense. And there we noticed some recent very interesting development from the autoregressive neural network and also the flow model. The basic idea is trying to perform the variational calculation on this statistical system. So basically you try to introduce a variational distribution, this Q theta, trying to match our target statistical distribution. And in the community, people are always using this distance measure to be the key error divergence. And this can be arrived at the minimization for variational free energy. So then this is familiar to physicists because we are applying the mean field theory, right? And there, just the variational answers is quite limited from the simple mean field calculation. It's usually limited by the factorization assumption or some other assumptions. And again, recall the universality theorem, we can introduce the neural network to provide a much more powerful variational answers. Meanwhile, it can guarantee the tractability, means we can evaluate these entropy terms easily for any kind of the sampled configurations. And in this work, people showed we can generally decompose this target distribution function into a series of conditionals products. And for each of these conditionals, we just use a neural network to represent its probability. Like for Ising system, you let it to represent its spin up or down that probability. And we further generalized this concept into a continuous system. And we first demonstrated on the XY model where the spin will have continuous variables. and we introduced such a mixture, continuous mixture autoregressive network using a beta distribution to represent the network output. And we demonstrate it can work very well in evaluating the thermodynamics for this system. And also we can get the access into the free energy. Meanwhile, the vorticity, this vortex structure, can automatically emerge from such a variational calculation. And our estimated phase transition point for this KT transition is also in a very good agreement to other Monte Carlo calculations. And here shows that our reconstructed variational distribution shows a very good similarity to the vortex structure for some randomly chosen examples. Okay, then about some inverse problem solving. So in this work, we showed we can use deep learning to perform the in-medium heavy quark interaction reconstruction from lattice QC data. So here the object is the bottomonium, it's the bond state of B and anti-B quark. And because it's having a very large mass and the relative velocity is very small, so usually we can have the effective non-relativistic description for that. And people always say this can provide us a smoking gun for the QGP formation. And this can provide us a calibrated QCD force. Like in vacuum, you have a well-defined baseline. We can use such a corner-like potential to describe its vacuum measurement of the spectrum. And when we put it into a finite temperature or density medium, by supporting the medium modifications on this interaction, we can try to get some information about the medium itself. That's why we're taking this as the smoking gun for the QGP formation. And naturally, we expect the color screening can happen to weaken this interaction. And some recent effective model calculation also show that the interaction of the heavy quarkonia inside the medium can also develop a non-vanishing imaginary part manifested as this thermal wave. So this is related to the Landau damping or the color singlet to octet transition. And in this work, we're taking some very effective empirical picture. We suppose the potential model is working, and then we're using such a reduced two-body Schrödinger equation function to describe the heavy bottomonium. And by specifying the complex valued interaction, this potential, we can get the complex valued eigenenergies, that's the mass and the thermal weight. And recently in Lattice QCD, people released some measurement of the bottomonium's in-medium spectroscopy for different temperatures and up to 3s and 2p states. That's for the first time we have such 5 lowest lying states in medium spectrum. So naturally, we want to figure out what kind of effective potential would this in-medium spectrum implies. So we tried first using the potential expressions on the market. That's usually using the perturbation-based calculation, but the all field, even though we try to tune whatever the alpha or the mean, the screening mass. So this motivates us to ask the question, given this in-medium spectroscopy, how we can unbiasedly extract the effective potential from this spectroscopy. So this is an inverse problem again. And we developed a deep neural network based approach. And to be different from the supervised learning strategy, here we are performing, you can call it a differentiable programming strategy. And the deep neural network is introduced to be only the unbiased representation for this potential. The input is the temperature and the distance between the two quarks, and the output is the values of the potential for their real part and imaginary part. Then we couple this DNN represented potential with the Schrödinger equation solving, so we can convert this potential to be their in-medium spectroscopy, their mass, and the thermal wave. Then we compare those values to the Lattice QCD released results, use the chi-square to be the guidance, trying to tune the model parameters here. And gradually, this network represented potential can match the final Lattice QCD measurement through this Schrödinger equation solving. And to perform this optimization, we did the linear response analysis. In the end, this just arrived at the Hammer-Feynman theorem in calculating the derivative between the mass and thermal width to the potentials. Okay, I will be more fast. And I will skip this proof of concept test, show you directly the result. So here shows you that our network represented potential can indeed match very well simultaneously the mass and the thermal width at different temperatures. That for the first time we can achieve it. And here on the right, you see the network represented potentials. To be very different from some other potentials on the market, like from the perturbation calculations, our reconstructed potential shows a much more strongly coupled nature. So basically, this would indicate we have to change our thinking mind in understanding medium heavy coconium from the static screening dominated picture to a more dynamical picture, because this imaginary part is much more larger compared to before. I will flash out this spectral function reconstruction from the Euclidean correlator. Again, this is utilizing similar strategy under the automatic differentiation strategy. Use neural network to represent the spectral function, and using this gradient descent algorithm, trying to match the finally observed Euclidean correlator. As we show that, this can give us a very good job compared to the MEM, the classical maximum entropy method. We also show this can work in the realistic hadron medium spectroscopy cases. Then about the neutron star sector. So we know that there is the one-to-one mapping between the macroscopic matters property to the macroscopic structure information of neutron star by solving this two-way equation. So given any equation state, we can solve the two-way equation, get the mass radius relationship. And now from the past decades, we accumulated many observations for the neutron star masses and radius, but they are just very noisy. We can only get this contour, that's the likelihood. So from there, how we can get knowledge about the medium microscopic, their matter properties, their equation of state. This is inverse problem again. And we are taking such a differentiable programming strategy here. We use two neural networks here. So one is to replace the two-way solving process. We call it a two-way solver equation, the two-way solver network. So this can be trained in a supervised manner. And we further test this trained network indeed works very well on whatever a different testing equation of state or on some physical model equation of state. And once this two-way solver network gets well trained, we fix the weight parameters of this network and perform the variational calculation on its input. So the input is the equation of state. This equation of state is represented again by an equation of state network. So we try to tune this equation of state network parameters to let the output of this two-way solver network to match the astronomy observationals. So on the mock test, we showed this works very successful, even though we include some noise. And on the real data set, so here shows you our result. The red band is our reconstruction using the current accumulated observational data for mass and radius of neutron star. So basically, we have a compatibility to other constraints, for example, from the chiral effective field theory or from the other Bayesian analysis and the recent supervised training, for example, from Fukushima. So we have very compatible results. Meanwhile, our band is a little bit narrower compared to others because we are having some constraints on this low density region for the equation of state. And shown here, this is the speed of sound square. Again, you see this trend is having some very stiff trend in the high density equation of state. So with that, let me go to the conclusion. First, we demonstrated that the physics of early time dynamics indeed can survive until the final state information heavy enclations. And this can be decoded back using machine learning. So that can help us to bridge the experiment to theory. And for inverse problems happened, for example, in Lattice or in neutron star studies, we can use deep neural network using the differentiable programming strategy to really give it a different hit. Okay. And the technical perspective is there are two different methods. One is this supervised training method. So you can provide some training data from your model simulation. So there, the prior of our physics knowledge is implemented inside the training data. The other way is to couple our model simulation together with this chi-square fitting procedure. And there you can also introduce the neural network to be our unbiased representation. So I hope these two different perspectives or strategies can give you some inspiration in your own research problem. And with that, let me thank you. Let me thank you again. Thanks for your attention and thanks for the invitation here.
Huichao, are you speaking? I cannot hear you.
Yeah. No. I saw no raise the hand.
Yes, thank you for this very nice, interesting talk. I have a question on slide 11. Because we do have problem experimentally determining collision centrality.
Okay, cool.
Especially, it's not cool. It's a kind of a technical headache.
I mean, we can play some role there.
Yes. So my question is, did you check the energy dependence? So that is one part of the
That's a good question. That's a good question. We didn't check yet the energy dependence, but we checked the model dependencies. Maybe that's in the backup. We checked the model dependencies by providing a different simulation. In that different simulation, we modified one channel for the hadronic rescattering. And there, the multiplicity would be a little bit different. And we showed that using the PointNet-based model, still we can achieve a better performance compared to the simple polynomial fit. But back to your question, if we do it on a different energy, I think we also need to provide some data on a different energy as the training set. With that, we can, because anyhow, in experiment, when you try to define the centrality, you are running some Monte Carlo global modeling. There you have the energy dependence, right?
Yes, we noticed experimentally this bias is less for high energy collision.
Yes.
It's very severe for low energy collisions. And the energy dependence, we also noticed actually this is also the observable dependent. For example, if you do just the mean value cross-section measurement, it's this correction would apply, no issue. But imagine we do high order correlation measurement. And we don't know how to get rid of it at the moment.
Okay.
Yeah,
I think the advantage of utilizing this PointNet model is you can rely on some microscopic transport simulation, and within that framework, you can get that unique mapping event by event from the final state information to the impact parameter. This is definitely possible.
I don't understand how do you do that? Can you go to slide 11?
Yeah, sure.
Yeah, if other question come up, I can stop, so I can talk to you later. So for example, on the top right plot, we experimentally select a cut basically on this particle numbers, right? We make a horizontal line. Let's say we cut on 400.
Yes.
But it's nature. This is the physics itself. This 400 cut corresponding to impact parameter, let's say from 0 to 5 or 4.5.
Yes, because you are using an average perspective. This is a histogram, right?
Yes, but you cannot. Yes, that's what I'm saying. For event by event, high order correlations, this averaging doesn't.
That's right. That's right. So the B is very important in evaluating the initial volume when you do the fluctuation analysis.
Yeah. So that maybe we should discuss in more detail later.
Yeah, later.
Yeah.
Kenji, please.
Yes. So thank you very much. Very nice talk, and I really enjoyed it. It is really a fantastic talk. And my question is about the speed of sound. You showed some overlaid result inferred from the heavy ion data, and also the astrophysical. Yes. And my question is, from the astrophysical observation, the information is about the matter in beta equilibrium. But the heavy ion collision creates a matter, almost symmetric nuclear matter. And so their isospin content seems to be quite different. But so did you make some correction so that you can make some reasonable comparison, or is it just a naive or some comparison in a naive way?
It's just naive comparison. This is just taken from this paper from Luciano here in Frankfurt. You are right. So they are different in their matter properties, but we just compare their speed of sound in this region, even though the temperature might be different.
Nevertheless, if I read so this data correctly, so your result suggests some peak structure, right? Almost around the same density.
Here, the stiff. So if we use the full observables from the flow and the mean MT, the reconstruction should look like here. That's very stiff.
Mm-hmm. Okay, that is extremely interesting, because recently with Larry McLellan, we discussed that peak structure comes from the almost conformal nature of the matter. So if the system approaches a conformality very quickly, it produces such a peak structure. So the conformal indicator is actually the internal energy minus 3 times pressure. And so if you make such a plot, that should be quite easy once you have inferred thermodynamics. Then it is I think quite interesting to see such a quantity from your inferred data. That's just a suggestion.
Okay, thank you for your comments. Yeah, actually here I would say if we remove the 2 points of the MT, then sorry, not removing. So if we include these 2 points of the mean MT, the reconstruction should get some compressment. That's why you see the mean MT is a little bit enhanced. So the expansion is not that much. Yeah.
Okay. Then so it means maybe so you have a huge uncertainty, and so this peak structure is not yet reliable. So is that what you mean?
No. I mean, if we remove the 2 points, the reconstruction looks like here. That might indicate a phase transition, but might also indicate there's some tension for this measurement. This measurement might be not so reliable, or the model we are using here, the URCMD, is not complete in describing the data. But this red curve is what the current data, the full data, can indicate for us. So we are assuming these 2 points are reliable, then the compressment of the fitting, the chi-square fitting, should give us such a red curve, even though that's not describing very well this high energy part, but that's kind of enhancing the mean transverse expansion to give you such a very stiff equation state. But that really depends on the data's quality and also the model's quality. Yeah.
Okay, I understand. Thank you very much for clarification. Okay, thank you.
Kenji, don't go away yet. You said that at the beginning, when your question, you said that you can do extrapolation from a symmetric matter to.
No. That was my question. Okay. I thought that because so 2 data are overlaid on the same plot, and so I assumed there was some way. So he invented, but so this is just a naive superposition. So
right. Yeah, this is also another important question I have in mind. How do we connect heavy ion collisions to out there? So yeah.
So we should make a caveat here. So there are some differences, but we only compare their density dependence.
Yeah, but could be fundamentally different.
Yeah, you're right.
May not be comparable. So. I don't know.
Yeah, so especially the phase transition nature can be very different. So if you see a nuclear matter, the symmetric nuclear matter has a liquid gas phase transition that is first order. But if you see a pure neutron matter, there is no such a phase transition because a pure neutron matter is not a self-bound system. So the property is very, very different. But of course, at such a very high density, in which maybe the quark degree of freedom might be liberated, then there might be some universal feature that cannot be, of course, excluded. So maybe it is reasonable to put the same data on the two data on the same plot.
Yes, so from the statistical point of view, so we get such a result that's for the very high density region, and we just very naively compare it to this constraint from the astronomy, but we cannot guarantee they share the similar nature. Yeah, you're right. Yeah.
More questions? I have a question. In one of the slides, you actually show that you extracted a smooth potential for the heavy quark from the individual spectrum, right?
Mm-hmm.
I'm wondering, how do you realize such a technique?
Okay, I think you asked a similar question when I give a talk in Beijing University. Basically, we're using neural network to represent this equation of state. And this neural network is introducing a functional format. So the input to this functional is the temperature and the radius, and the output is the value of the potentials. So by definition, this is a smooth function, right? Mm-hmm. And you have the tuning parameters, that's the weights and the bias of this network. And the tuning guidance is trying to let the final output from this Schrodinger equation solver to match the lattice QCD data. And you always guarantee that you are accommodating this lattice measurement. And once you are ended with your training, still you're having a smooth representation here. So that's by definition smooth. And we tested it on some, I didn't show this. I don't know why this is not doing the animation, but there's an animation that if we do a very simple verification of this method on the simple harmonic oscillator quantum system. So suppose this is the ground truth, this dotted line, the thick dotted line is the ground truth. It's a harmonic oscillator, and we use that to solve the Schrodinger equation. We get the 5 eigenvalues, the first 5 states, their eigenvalues. This is the numbers. We only use these 5 numbers as the input to our algorithm. And we try to tune the network represented potential. And in the beginning, it's far away from the ground truth, this straight line. And gradually, you will observe this will match to this ground truth. But there are some deviation happened, but only at the very high distance region. That's making sense. If you recall this Hammond-Feynman theorem, we know that the interaction values beyond these 5 states, their wave functions coverage is here, right? So the interaction values here will not influence the eigenvalues for this lowest 5 states. And in the end, we also get a smooth function. Just you can get the uncertainty to be estimated around your reconstruction, like I showed here, maybe. Within the information that you can deliver, your uncertainty will be very narrow, but beyond that information delivered region, you will get a very high uncertainty. You just estimate your uncertainty using the Bayesian perspective. So the answer would be, by definition, this representation is smooth, but you can get the uncertainty depending on the range where you can believe your reconstruction.
Mm-hmm. Okay, I didn't see more questions. I have another question. You actually shows the implementation for deep learning to lattice calculation, right? I'm wondering how far away, I would like to hear your comments, how far away for such machine learning application for realistic lattice QCD simulation, and what is the difficult for such implementation?
Okay, that's a very comprehensive question, I would say. I'm definitely not the Lattice expert, but my point of view is, my understanding is in Lattice calculation, there are 3 different computations. One is the field configuration generation. That would be the largest barriers or largest effort you need to put. You need to run a lot of the simulation to generate your field configurations. And in this direction, currently, there are some development using the flow models, for example, from MIT, FIAS, Shanaha. So they are pushing this direction into the real Lattice, the gauge field simulation. For currently, it's only in the, I think it's only in the SU1, right? Not in SU2 yet. And maybe later, I don't know. So they are trying to push it into SU2 and SU3 quickly. But there is still not that efficient because you need to guarantee the symmetries to be embedded inside the neural network. Once you change your network structure to really respect those symmetries, the simulation efficiency is not that high, but it's already much better compared to the classical MC or hybrid Monte Carlo or whatever, the traditional method. It's already much better there, but not satisfying if you really want to let it to be a game changer. Then the other direction in Lattice related study is you generated many field configurations and you want to evaluate some observables. You want to investigate its topology structure, for example. And that's about some regression task or some pattern recognition. So around this direction, definitely you can play around your learning algorithm, trying to do some tasks. Then the third direction is such kind of inverse problems. For example, the spectral function reconstruction or this the real-time dynamics reconstruction using some Lattice data. So you want to connect your Lattice data to some phenomenological models. So how you efficiently make this connection. This you can tag. You can try this machine learning perspective, I think.
Okay, thank you. I didn't see more questions from the audience. Maybe it's time to close the talk. Do you have an announcement?
No, but if nothing, let us meet again next time and next Tuesday. And thank you for coming. And thank you, Kai, for giving this nice
Thank
talk.
you very much.
Thank you.
Thank you. Bye.
Yeah, bye.
Bye.
See you. Yeah.
Bye.
We had about 112